Let's begin a new series of problems where we're going to use entropy as a property to solve various kinds of thermodynamic problems. 1 pound mass of water in a piston cylinder assembly, initially a saturated liquid at 1 atmosphere, undergoes a constant pressure internally reversible expansion to a quality of 90%. Determine the work and heat transfer, each in BTU. Sketch the process on PV and TS coordinates. Associate the work and heat transfer with areas on these diagrams. So let's lay out our storyboard to solve this problem. Begin with a schematic. We've got a piston cylinder assembly filled with water, and it's oriented vertically, which I always do to show that it's a constant pressure process. And I'm going to draw a boundary around all of the water molecules inside the piston cylinder apparatus, and they are going to define the system that we're going to analyze. So what we're given is that initially the water is a saturated liquid at a pressure of 1 atmosphere, and its mass is 1 pound mass. It's going to expand until the quality is 90%, and it does this at a constant pressure. Let's look at how we could model this. Clearly, we're dealing with a closed system, and as always, we'll neglect kinetic and potential energy changes as being insignificant. We're given that the pressure is a constant, but I'm also going to assume that the temperature is constant, and the reason is we start out as a saturated liquid, and we expand to a quality of 90%. Well, all of this process takes place at a constant pressure of 1 atmosphere underneath the vapor dome. Well, in that situation, the temperature is also constant. We were also given that the process is internally reversible, and that means that there is no entropy production. And we wish to find the final pressure and the work done by this process. So let's begin in the water saturation table at a pressure of 1 atmosphere. And we just see that at this pressure, the saturation temperature is 212 degrees Fahrenheit, which is 672 degrees Rankine. I'm going to grab values from this table for V sub F and V sub G, S sub F and S sub G, because the entire time of the process, the water is either a saturated liquid or a saturated mixture. So now let's get important properties for state one when it's saturated liquid. Well, its specific volume is just V sub F, and that's this value that we took from the table already. And S1 is S sub F, and so we have that value. And for the state two properties, it's a saturated mixture at a quality of 90%. So V2 is just V sub F plus the quality times V sub G minus V sub F. We have all those values. And V2 is 24.1217 cubic feet per pound mass. S2 is just S sub F plus the quality times S sub G minus S sub F. And we have all those values as well. And we see that the entropy at state 2 is 1.6122 BTUs per pound mass R. Now we want to calculate the work done by this process. Well, we know that work is the integral of P to V, and for a constant pressure process, it's the pressure times the change in volume, which is the pressure times the mass times the change in specific volume. Well, we have all of these values. The pressure is 14.7 pounds force per square inch, and I'll convert square inches to square feet. The mass is 1 pound mass, and we have values for V2 and V1 in cubic feet per pound mass. I calculate that the work is equal to 65.6 BTUs. Now let's calculate the heat transfer that takes place during this process. We know that for an internally reversible process only, Q, the heat transfer, is the integral from state 1 to state 2 of TdS. And if we have a constant temperature process, then the integral of TdS is just the temperature times the change in entropy. And we can write that as the temperature times the mass times the change in specific entropy. So what we see is that a process going from state 1 to state 2 that is internally reversible. We know that the process follows this line, this horizontal line between states 1 and 2, and the area under the curve is the heat transfer Q. So now we can say that Q is the temperature, 672 degrees Rankine, times the mass, 1 pound mass, times the change in specific entropy, which is S2 minus S1, and we've got values for that. And I calculate that the heat transfer that takes place during this process is 873.7 BTUs.